at ColibriTD, and as a moderator we'll have the pleasure of welcoming again Fanny, Bouton, Quantum Lead and Startup Program Leader at OVHcloud. Please give them a warm round of applause.
Hi guys. I think we can start directly to ask you, Laurent, what is MPQP, what is it used for?
Bonjour Fanny. Bonjour tout le monde. Donc MPQP stands for, it's English, yes, sorry. Multi-platform quantum programming. So, I mean, if you look at what Colibri goal is, we want to democratize access to quantum computing. And we really want to accelerate. So from the project to the deployment on the machine, it has to be faster. We can't do 2-year project for one machine, 2 years project for another machine. Like we say, we want to accelerate. So what we realized when we were doing our R&D development is that every kind of framework had some specificities that we needed. Qiskit, Tkinate, Circ, etc. And also, we were facing more than 70 potential hardware providers. Therefore, we needed to have something which was quite generic, so we developed once and we deploy everywhere. That was really the goal and the aim of MPQP when we developed. And then we said, oh, maybe it could be useful for others, and we set it as an open source tool for everyone to use and give feedback on.
You want to develop a bit?
Yes, for me, MPQP is a very interesting initiative because eventually people don't want to know any details about the quantum computer. They want to use it for particular application, and it's super important for quantum computer builder like Quandela or others, just to know that they are part of something a bit bigger, something that is a bit agnostic. And then when we'll be talking about application, we don't want to have quantum scientists to develop algorithms. We want to have developers to develop application. And it's key that a platform like MPQP is there to help and to kind of democratize, as Laurent was saying, quantum computing.
Okay. How many qubits would be needed to run MPQP? Do we need to wait, or we can start now?
No, so our core research right now is on solving partial differential equations on simple models. So what we don't need that many qubits right now. On what few qubits are enough, because what we focus on is to develop the modelization of the problem, so the mathematical problem of partial differential equation on certain aspects into a quantum algorithm, and then we need to have the noise model. So that's really, I mean, what we want to be is less heuristic and more kind of try to prove that what we do is scalable. So we can start with few qubits, real qubits, not simulated qubits, real qubits on real machine, and then from the noise model we can prove that it can scale. That's really the aim of what we are trying. The core of our research is really to work with existing computer with a number of qubits. Then for sure, when you solve a 1D flame with 2 qubits or 3 qubits, you're not going to solve a 3D flame with it. You will need far more qubits, but not that many, and we need to start small to prove that we can scale. That's really the goal and the aim of what we are doing.
And if I can add on that, I think it's not only necessary that we start, important that we start now, but it's also necessary because a few qubits is what we have today. So we can say 5, 10, 20, 100, but it's time to move, as Scott was mentioning that before, out of the blackboard and to go to application. And to go to application, we need to find utility in what we have today and not to look at quantum computer as just quantum computer, but at computers. And for that, we need to see how we can use their power, which is fundamentally different than any classical computing, with 5 qubits, 10 qubits, 20 qubits. And if we cannot do that now, that means that probably we are on the wrong track. We'll be waiting for a billion of something that has not yet proven today.
Are photons particularly practical for MPQP, Jean?
So, of course, I would say yes. So, photons have very nice features. So, they don't decohere. The type of noise that you have in photons is very specific, and it's quite easy to predict what we get as an output. There's another thing with photons, so it's not really working on technically on what's called the Hilbert space, but on the Fock space, which is larger, which means that for practical application with few qubits today, we have the power of a bigger space to explore. than we can have for others. But so it's particularly useful from my perspective. But I would say that it's not necessary. So again, even if it was not more expressive, it would still be interesting to work with 10, 5, 20 photons as of today. The important is that you can test. So what is useful is that it's available, basically. If you can use a computer today with 10 photons, then of course it's more useful than using any other technology with 5,000 that will be available in 10 years.
Laurent, is it possible to run MPQP on the quantum computer acquired by OVHcloud?
We're working on it. There's two ways to do it, to be honest. There's some work. So, like Jean said, it's photon-based, so you have a very specific way of programming. You can do gate-based programming on photons, but that's not optimized. What our current work is to adapt to a photon-based approach, which is native, in order to really optimize. Because photons, as Jean said, it's not the Hilbert space. That's another space. That's another linear algebra to use. So that's a little bit more. It's different. It's not more complex because anyway, quantum is quite complex anyway. So I would say it's less or not complex. The complexity is the same. But basically, you have to think a different way. That's why we also want to. We want to also work with industry, with partners, in order to find the best project for that. That's also what a call from us. It's to find partners to really drive, because we are not labs. We do research. That's 80% of our work is research, but we are not labs. The end goal is to work with partners, industrial partners, to deliver solutions at the scale we can deliver today. So that's really a goal we have, to work with photon-based and also with some specific use case, because our belief is that there's some use case which will work really nicely with photons. There's some use case that will work nicely with pure gate-based computers, and other use case with other technologies. So basically, there's no choice to make today. The choice is to be made based on the use case, based on the partners, and based on the value we can bring. That's the key message to deliver. We are not like just testing for the sake of testing. We want to have real-world application today that scale over time.
And if I can add on that, on the fact that is it possible, I think we have the chance to have companies like OVHcloud that have purchased a quantum computer, a real quantum computer that is operating 90% plus of the time, and it's necessary to connect to it. So we don't have quantum computer is a very scarce resource. There is very few of them in France, available even more. And personally, so I'm working in a quantum company, and I'm working with amazing people, quantum scientists and quantum information people. And I'm just software guy. And in some way, I'm here to help. And it's when we have the chance to have this technology that is available, we do have to make the connection. And I know it's easy. So for me, doing software is my DNA, and it's so easy to connect to that. So it will be wasting resource not to give access to what is available and can be available today. So yes, it's useful, it's necessary, and we are committed to work on that. And in some way, it's easy just connecting. So software.
To conclude, to convince maybe new Future Alliance to join you.
So like I mentioned in the beginning, we have a project simulating a 1D flame, one-dimensional flame. Combustion is a complex process. I mean, you can totally do a complete simulation of 1D flame with classical computers. I'm not going to say that quantum will bring advantage, but we need to start. We are also looking at some fluid dynamics use cases and some specific fluids. Again, that's all around partial differential equations, which are our key topics. We have a few use cases around optimization, but basically the core of what we do is building a platform on partial differential equations for 1D flame, 2D flame, simulation, fluid dynamics, and so on, material deformation. That's the use case we concentrate on right now.
And can you just explain maybe, is it easy to set up on quantum computer?
Oh yeah, that's really the core of what we do. It's like in 5 minutes you have MPQP installed, you start to work on your notebooks, and you target any platform. So that's really easy. I mean, that's why we have partnership with OVH, and that's because we want to have that done in 5 minutes. remember, the goal is to accelerate quantum computing adoption. So not go into 2 years, 3 years, 4 years project. Do it now, test your use cases. Is it quantum compatible today? Yes, no, and you go forward. And you test multiple use cases. That's key to drive, because quantum computing will transform profoundly the way we do things. But we don't know exactly. There's some signs that some use case will be more favorable for quantum than others, but there's so many to explore, and we need to accelerate. So everyone in the room, acceleration is key, and go after. We have the chance in France to have a multiple hardware provider, photonic based, and it's key to work today on that.
And just to, on my side, to conclude and to echo the previous presentation, we need to try. And there is definitely, and the previous presentation was saying basically we need to try different use cases. Some of them you will get some advantage heuristically. Maybe you cannot prove that. But if you have not tried, you won't be able to know. On our side, we are more focused these days on working for optimization. So we are looking at MPQP with this particular angle, how we can solve some optimization problem, because we see that optimization is one of the key area where most enterprise, I think all of them, have issue. You need to optimize your agenda, you need to optimize your logistics, you need to optimize the way you deal with project. Optimization is something that we classically cannot solve. It's becoming so complex. As soon as you have more than few elements, then we have just classical heuristics. So why don't we find some classical quantum heuristic too to solve the same? So I think that optimization probably is one of the key area where we should try to test now.
Laurent, do you want to conclude, to convince maybe new Future Alliance to join you?
I mean, there's no risk, only rewards at the end of the day. I mean, we've seen so many for the more senior among us, which I am. Basically, we've seen so many transformation, cloud, data, Gen AI, and you name it. Quantum is just another one, and the one that starts today will be the winner tomorrow, if I can say so.
Okay, thank you, Jean. Thank you, Laurent.
Merci.
I hope you know
Merci.
a bit more about MPQP and you want to try. See you.